My name is Tristan. I'm a PhD in mechanical engineering in Imperial College London, and now in my third year of my PhD. So my PhD focuses on getting a better understanding of materials in a nuclear fusion reactor. So in a fusion reactor, we have what we call the tokamak, which is the shape of a donut. And inside this tokamak, we've got a very hot plasma, which is facing metals. And in my PhD, we're looking at joining the plasma-facing metal, which is tungsten, a very high melting temperature metal, to steel, which is a common material used to build the structure of the reactor. So national institutions have thought about methods to join those two metals, and we think that brazing is a promising method. So on my PhD, I'm actually focusing on understanding the brazing procedures, the limitation of joining tungsten to steel, so in this context of nuclear fusion. Joining materials and materials themselves is one of the three challenges that we're facing, that researchers are facing in nuclear fusion. So here we want to make sure that when we join tungsten to steel, we have a joint that will last over time and that won't fracture during the operation of the reactor. And we want also to better understand the fracture processes in those brations, which are due to the difference in thermal expansion of the two metals that we're trying to join. So hopefully by the end of the PhD, we have a better understanding of whether it's possible to join adequately those two metals together. And at the end of the PhD, whether it's a success or not, we know whether we can use brazing to join those materials or whether we want to use a different technique. One of the challenges I have right now is that, so during my PhD I'm making quite a few experiments and we're trying to better understand with those experiments the fracture behavior of brazed joints, so joining tungsten to steel, how they fracture. And to do that, we're doing experimental testing that involves some mechanical loading. So we're using weights to apply some load around the brazed joint, and we fracture the brazed joint. And when we do that, we're trying to measure how the crack develops, and also if there are any change of microstructure during the testing, which is done at high temperature. The problem with this testing is that it's mechanical testing, but actually in the reactor, all the stresses will be thermal stresses. So we've got two different sources of stresses. The mechanical stresses are used in testing, but the thermal stresses are the ones that are of concern in the fusion nuclear reactor. So one of the challenges is how to correlate the results that we get in the testing and apply that to predicting the life expectancy of components that are only subject to thermal stresses. So earlier, before my PhD, I did an internship in nuclear, but fission, so the traditional nuclear power plants that we know and can produce some of the electricity in the UK or in France. And I wanted to know more about nuclear fusion because at this time I didn't know much about it. So really the PhD was a way for me to better understand what is nuclear fusion and whether what are the challenges and how we can find as well solutions to those challenges. It's a bit different of what I imagined. I mean, you cannot, I think it's very difficult after getting a master to really know what a PhD is like. Some aspects of it, there were no surprise, but there were a few surprises on some part of my PhD. I didn't have much knowledge in experimental testing, and this is something I discovered, so I had no idea actually what testing metals at high temperature look like, and now I've got a better insight of that. Nonetheless, I know I'm making progress, but we're in a field where we have a lot of questions. Some PhDs are more follow a more simple path than mine. The news revealed that electricity production is becoming more expensive right now, and very high hopes for new methods of electricity production, so notably nuclear fusion, to bring back the costs and allow for societies to benefit from cheap electricity, and also electricity that doesn't emit CO2 in its creation. We don't have any fusion reactors that do produce electricity, and they're only experimental reactors. And we've got a few in Europe, and notably one in the UK, which is called JET, and which conducts experiments on materials, the plasma, and really trying to make fusion an energy of the future. There are three big challenges that need to be solved before we can really have a reactor that produces electricity. And those are linked to the materials, so this is related to my PhD, finding suitable materials that can resist the very tough environment inside the nuclear reactor. So this is the first challenge. The second challenge is when we talk about nuclear fusion reactors, we talk about tokamaks, which are donut shaped where we confine the plasma, and the second challenge is linked to this confinement, to this control of the plasma where fusion occurs. And the third challenge is linked to the production of tritium, which is an isotope of hydrogen, which is used as a fuel to produce this fusion reactor. When you're doing something that has never been done before, it's actually very hard to know where you're at. But still, we've got some timelines that are done by the different fusion institutions, and there are 9 different steps in the development, for instance, of materials. And depending on the material you're looking at, we're ranging from step 2 to 4 or 5. And we really need to reach step 7 or 8 to be confident that what we've researched or developed is actually suitable for the use in a nuclear fusion power plant. Even though the results are not always positive, even a negative result can be useful for the industry to better understand the future problems we might have with materials. My funding is part from the UK Atomic Energy Agency, which is a national institution in the UK that conducts research in the nuclear sector. And it's mostly funded by the government, so taxpayer money. Very different the other nuclear projects in the world, notably nuclear fusion projects. One well known is the development of the ITER reactor. So it's an international project that tries to develop, is building right now, an experimental nuclear reactor in the south of France. And this is being funded by a total of more than 30 countries around the world, notably Europe, the United States, China, India, Russia, and other countries. I quite enjoy the simulation part of my PhD, so trying to use computers to better understand the properties of materials. I didn't know actually where to go after my bachelor, and I thought that energy was a very interesting thing, because in the society we live in today, we need energy to do anything. I really discovered nuclear during a master research internship. I was always learning the fundamentals of physics and mechanical engineering, and those fundamentals are used in any technical problem in the nuclear industry or elsewhere. I was in high school. I got good grades in geopolitics. I was enjoying the learning process, understanding the links between politics, geography, trying to explain why some countries are more powerful than others, trying to relate that to their history. So it could have been a future for me, but I always also had engineering in the back of my mind, and I chose it later. Energy and geopolitics are much connected between each other, because if you look at the most powerful countries today, so emerging basically from the Second World War and the Cold War, the United States, it's a country that has enormous reserves of fossil fuels. I just want to point out that it wasn't a clear path. I mean, now I'm in Imperial, I'm doing a PhD in a very promising field, but really before getting to this point, there were a lot of hesitation in the path to get there. Some things did work, some others didn't. It was really with better understanding that I got to know myself better and also know what I wanted to do after high school. But now I still have this question of what I want to do after the PhD. Final internship during my master, so it was actually a 6-month internship, and I decided to do it at the CEA, which is a French national research institute that works on nuclear. So I did a research internship on the thermal conductivity of the nuclear fuel, and I didn't know not much about nuclear at the time. And apart from this research that I was doing on simulating actually, so the thermal conductivity of a specific arrangement of the nuclear fuel, it allowed me also to understand a bit better how a nuclear reactor was working, how much electricity we produce, how you control the nuclear reaction. So it was actually a very interesting internship in the sense that I could also expand my knowledge on this source energy production mean that is widely used in France. I didn't know whether I wanted to stay in academia or go to industry, and the PhD really allowed me to choose both options in the case. I mean, I didn't know at the time, so it was basically maintaining those doors open. And also a lot of jobs in the research institutions, they require PhDs, so I thought it was the right choice for me. So the main drawbacks of the PhD is, the main one is probably the length of it, so it's 3.5 years, 4 years. And it can be very tough because sometimes you're working on your own, not in collaboration with other people. Of course, you've got supervisors that can help you in the project, but you're the expert in your own PhD topic, and you've got to produce the results and the experimental procedure that can answer your PhD question, PhD project problems. I would say that's the main drawback, but there are many, many advantages of doing a PhD, I think. Some of them you meet quite, I mean, I know you work on your own on your PhD, but you've got people around you that are working on different topics, and I quite enjoy, especially in Imperial, meeting those people, trying to understand what they're doing, what is their thinking on their point of view on their field, their problem, and it can actually allow you to understand different fields of engineering. So having friends that doing maths allows you to understand a bit better mathematical research. In nuclear, I've got some friends that work in different fields, so in chemistry, working more on the materials, working on ceramics, and basically I get to understand a bit more all that they're doing, and in the end it allows me to better understand engineering as a whole. Also, the PhD, I mean, it's long, but it's also, if you're not sure about what you want to do, for instance, going to academia or industry, it gives you 4 years to think about it. And I would say that overall it allows you also to meet people from both the academia and the industry, and better decide for yourself of what you want to do in the future. For me, it was a good decision doing the PhD, and I do enjoy it, even though there are difficult days sometimes. But I think to better know whether a PhD is worth for someone, you've got to ask that question quite a few years after the PhD. Everything is a risk. I mean, if you do PhD and you don't enjoy it, I mean, you took the risk and it wasn't beneficial for you. That doesn't mean it's the end of your career. You know, you can bounce back and do something else. But also, some people start in industry and they actually find that industry is not for them, and they come back to academia, and that's fine as well. Like there's a time where things are difficult, and you trying to bounce back to make things better. That's something that everyone should do, whether they choose to do PhD or not.